think I mentioned that those commercial cameras were rather expensive, particularly because they have such good time resolution. Okay, the shorter amounts of time that you want to display, the price goes up. So what we're going to try to do, what we are going to do, is to determine the speed of a .22 caliber bullet. So we photographed one doing things to various subjects, but we didn't actually have proof of how fast those bullets were traveling. Well, we do have kind of a gut feeling for how fast they're moving, about 1,000 feet per second, but it could be faster, could be slower. So we're going to use a street camera to help us determine what the actual speed of those bullets is. It'll be a film camera, so you'll need to provide film.
Does it matter what speed?
Probably 400 speed film.
And each of us are going to record
Each
this?
group.
Each group?
Right, will get their own chance to work with the camera. So, as you're setting up this project to determine the speed of a .22, you might want to think about what kind of a stopwatch would be useful to have. What kind of time resolution the stopwatch would have to have in order to be of any use. Obviously, a little, one that you push the button on and so on is not going to make it. If this bullet travels, a distance of 1 foot in 1/1000th of a second, it would be a good idea to have a stopwatch that is able to measure accurately in terms of 1,000th of a second. So the little hand scanner digital array is not going to cut it, because it can't look at the array fast enough. There's another camera that I have, that is a digital one, that looks at a line every 3,000th of a second. It's a digital camera, so it'll take 1 line, 2 lines, 3 lines, okay? And this then would stand for 1,000th of a second. Well, that's not very useful either, because there's not enough data there. It would be, I think if we had a film camera, we have 35mm film, where that goes, and we could move this at 1,000 inches per second, right? In that case, 1 inch of film is equal to 1/1000th of a second. Now that would be pretty useful. Okay, but how do we make the film move that fast? Well, there are many ways. It's either move the film or move an image. The big pie-shaped gray camera that's sitting outside of this door does the motion by moving an image. Well, that's getting a little too sophisticated. So what we need is a camera in which we can move the film at about this speed. It's not going to be a 35 where you're rewinding the film. It doesn't go fast enough. So what we'll use is something called a rotating drum street camera. In high-speed photography, rotating drums are used for a variety of applications. In this case, we have a drum. And we can drive this drum at some rate, and onto the outside of this we'll tape film. So So the camera that we're going to use has a drum circumference of 12 inches. In front of this, there is a slit. So now we have the two ingredients necessary for a street camera: a stationary slit and film moving behind it. Now, the thing about the drum camera is that once it's made one revolution, it's exposing photosensitive material again,
Should
right?
I stop it?
Well, no, you don't want to stop it. No, it's just that if you make the background against which you're going to put the subject black, in that case this could turn as long as it wants and it's not going to get exposed, right? So, but if your subject has some light to it, in that case that will expose. So what we want to achieve in this camera is to have the film move past that slot at 1,000 inches a second. Well, how do we do that? We power up the motor and we'll make it turn. But how fast should that drum turn in order to achieve 1,000 inches a second? Well, let's see. Anybody can help me? Well, let's put it this way. If we turn it once a second, in that case we would move 12 inches per second, right? All right, we could do this the long way. It's okay. If we turn it 2 RPS, we'll go 24 inches per second. At 4 RPS, we go 48 inches per second. At 8, right? We're doubling it every time. So now we're at 96. At 16, we're at 100 and...
Would you just divide the 1,000 by 12? If you want to go 1,000 inches a second, you would divide it by...
Somebody in the audience here said, divide 1,000 by 12.
Right.
And that'll give you the RPS.
Okay.
Yeah, absolutely. Yeah, you shouldn't be scared for me. Yeah, I mean, I was waiting for somebody to say that. But if you weren't going to do that, you could do it the long way, right? You could do it, well, I'll double this, and eventually I'll get to 1,000 inches a second. We could take 1,000 inches, divide by inches per second, right? And divide by 12 inches, we end up with 83 something
83
RPS. Well, typically, rotation rates are given in RPM, not in RPS. So how do we end up with RPM? Multiply them 60, and anybody can tell me what that is? I could do it, but
4,998.
okay, this reminds me of my Australian friend. 4,998 point something, right?
Well, I went to 83.
Oh. How about if I just round this up to 5,000? Would that be okay? $5,000 is a lot easier to work with than 4,998. So anyway, we make this drum turn at this rate, RPM, and lo and behold, the film moves through the system at 1,000 inches a second. So 1 inch will be 1,000th of a second. So now we're going to put an image of something on here. Well, one thing that we need, since we're going to be measuring this bullet traveling in terms of feet per second, we need some kind of a scale of distance, because the camera, as it looks out there in space, it doesn't know how big anything is. So we're going to put a scale on here, and okay, in an imaginary way, we'll use 2 lamps, okay? And we'll put them 1 foot apart. So if we include these in the camera, so there'll be one here and another one there, okay? And they're going to be there for at least one rotation of the drum. When they do that, they will leave a trace. Okay? And it goes like that, right? So we'll have two lines, and we'll know that the distance between them is a foot apart. There is our scale of distance. And our scale of time is the fact that we're rotating at this rate, which gives us this, which is what we want. Okay, so now we're going to take a gun and shoot a bullet right through the lamps. And we're not going to do that. But you can imagine you could do it, right? So the bullet travels this way, and it travels between them in about 1,000th of a second. And as it travels from one to the other, the film is moving. And let's say the film is moving this way. So it's at this lamp first, and before it gets there, it's at the edge of the film, and then it leaves a diagonal line. Remember that graphic from the slideshow that had the diagonal line in it? And we talked about how you figure out how fast things are moving? Well, it's the same thing right here. So we could change the scale, for example. We could change the distance, or we could change the distance between the two images of lamps so that they're smaller. And so, but we will always know that the distance between the lamps is 1,000th of a second. So if the distance is, let's say, half as big, okay, in that case these lines are over here. Now what happens to the line that the bullet will make, the trace the bullet makes? It should be, it still has to go from one wire to the other in the same length of time, right? But before, the time is right here. So now the slope has diminished. It's because now you're looking at a larger area. And I'll draw this horizontally in just a second. Now because a drum camera like this, and we'll run it across another one next week, because it is a drum camera, it has some very useful characteristics. One of them is that the speed at which this recording medium is moving is constant, so that you can tell that any place along the length of the record, a certain distance along the film stood for a certain amount of time. In some other camera systems, that's not the case. And the other is that the camera is, as they say, unlike you all, always alert. That means it doesn't need a synchronization device in order to make a picture. If an event happens, it gets recorded. So they're always alert. And that's because, this slot is always open. And as long as the film keeps moving, if something happens, you see it. If it doesn't happen, you don't see it. From a high-speed photography point of view, synchronization is always a major problem. Drum cameras solve that. To achieve the kind of time resolution that this camera has, which is an inch every 1,000th of a second, with a digital system, would start to get pretty expensive. Okay, here we're doing it very simply. And I'll show you the camera that we'll use. I put it here somewhere. Oh, there it is. Very sophisticated. Very expensive. There's the drum. Okay, and there's a motor to ride the drum. And there's a slit up here, and the lens, and a light-tight box. All the cameras that you see, all the street cameras that you see, essentially do the same thing as what this will do. Some do it faster, some do it slower. This is someplace in between. But getting a time resolution of a thousandth of a second per inch is, I think, pretty significant. So now let's take a look at what I do with this thing. You know, what this might look like if we turn it 90 degrees. Because typically that's what you're going to do. I'll have a strip of film. It'll be 12 inches long. It has a sprocket holes in there, so I'll leave them out. In here, there will be a couple of lines that are going to determine or show us the position of those lamps. But instead of using lamps, we're going to use something else. But we'll know that this distance is 1 foot. Okay, and we'll know that in this direction, 1 inch is 1/1000th of a second. And each team is going to be photographing a long rifle, 22, and a short. So you'll have 2 traces on here, if you're lucky. They will be clearly separated. If not, it doesn't matter. But anyway, there'll be 2 lines. One like this, and the other one like this. Maybe. They could cross over each other. They could be over the seam because, you know, where the film is joined together. The image could fall across the seam, but it doesn't matter. You just join them together. So you have a couple lines, and eventually you have to make a determination of, well, how fast is the bullet moving? Remember, velocity is equal to change in distance divided by change in time. The change in distance for us is the distance between the 2 markers. The change in time is this dimension right here. Suppose that we measure this, and it turns out that this is 1 inch. How fast is the bullet moving? Well, how far did it travel? A foot. And how much time did it take it to do it? So the speed of the bullet is 1,000 feet per second. Falling off a log, right? Pretty easy. Okay, well now let's take a look at the other bullet. It also traveled, okay, a distance of 1 foot. However, it took it that much time. And let's say you measure it out, and it turns out to be that this is 1.5 inches. So was this bullet traveling faster or slower than the first one? Slower. It traveled 1 foot in how much time? 1.5 1,000th of a second. Or, this will be 1,000, right, divided by 1.5, which is, what, 666 and 2/3? I believe. Pretty neat. If the distance from the time that the bullet is at the first wire and the second one is less than an inch, it's traveling faster than 1,000 feet per second. Suppose that the distance is, you know, it's this fast, and the distance here is 0.5 inches. In that case, how fast was the bullet traveling? Quick thinking here. Half the time for the same distance. Right? No, the other way. You went the wrong way. 2,000 feet a second. Right? Because now you're saying 1 foot divided by 0.5 1,000ths, right? So you still get 1,000 at the top, but you're dividing by 0.5. So that is 2,000. Right? Now you'll be lucky if you get results that look like this, you know, half and 1 and 1.5. It'll be something in between, I'm pretty sure. Are there any questions? I might ask, well, how are we going to make sure that the drum is turning at the right speed? Obviously, it's for precision results, it's critical, right? Well, there are a couple of ways that you could do it. I had to come up with another third method. One of them is to use a flashing light, a stroboscope. Okay, which a calibrated stroboscope. You know, it can't be just any stroboscope. Something that tells you that the flash is flashing at a particular rate. And then if you use the stroboscope properly, in that case, that will tell you what the RPM of a rotating object is. We'll get into that later. But it's kind of a, again, as I said, falling off a log answer. Oh, use a stroboscope. Car people use it all the time, don't they? The other one is to use something called a phototachometer. Car people use those, I think, but not quite as extensively. I'm not going to draw it. A phototachometer simply measures the time between pulses, light pulses that get to the photodetector. So it's kind of a light meter, and it looks out there. It says, well, I see a flash of light, and I see another flash of light. I can determine what the time between them is and give you a readout in RPM. I made one of those. I don't have it here. It kind of looks like this, but it works. Okay. And you can calibrate it in various ways. I use the neon tubes to calibrate it against, but other ways of doing it are doable also. So a phototachometer will tell us how fast the drum is turning. And again, the phototachometer or the stroboscope becomes a standard. We're not going to question whether the stroboscope, which we're not going to use, or the phototachometer is calibrated or not. We're going to assume, yeah, the numbers they're giving us are accurate. There's one other aspect to this particular problem, and that is that we have a bullet here, which is about 10 millimeters long. And it's moving at 300,000 millimeters per second. And remember, I think some time ago we talked about, well, the review exam had a question about a subject becoming its own shutter, right? So we have a situation here where this bullet is not going to be in the same place all the time. It is going to deliver an exposure time of 1/30,000th of a second. Well, with a 1/30,000th of a second exposure time, we're probably going to need an awful lot of light in order to make a record of that moving bullet, okay, that's of any significance. So the way to do that is to pour a lot of light onto the bullet. But you put lots of light on the bullet, you're also putting lots of light on the background. Right? But the background isn't moving anywhere. Well, that means that somehow or another you have to decrease the light that's falling on the background so that the lots of light that falls on the bullet is able to make an impression on the film. So we're going to use, black velvet background, but also prevent light from going to it. And how do we get lots of light to do this? Well, we're going to use a studio flash that's going to put out lots of light. We'll put it close to the flight path of the bullet. And the neat thing about using a studio flash is that it has a fairly long duration, maybe 1/100th of a second or so. And for that time, it puts out lots of light. And the good thing is that we don't need to worry about double exposure of the film. Because even if the flash lasts for 1/100th of a second, this drum takes 1/80th of a second roughly to make a turn, right? So the flash would last that long, and that means we don't get double exposure. But the background is still going to be lit up. But anyway, we minimize some of the background exposure by using a narrow slit. But if you use a narrow slit, you have difficulty making the bullet travel along that slit. And what was your question, Ian?
How are we going to set the flash off?
We're going to use a sound synchronizer.
We'll use the same thing that we used before?
Yeah.
Okay.
Yeah, obviously we need to set up the synchronizer. So the bullet is going to travel this way. Here are two lines. And we need to put the synchronizer someplace over here, so that by the time the bullet gets to the first lamp, for example, the flash will be at full intensity. So it'll come up like this, and it'll decay like that.
So it'll just take some time to get that synced properly.
Yeah. See, in the olden days, we could do the thing about taking the film and then processing it by hand and then just looking at, are we getting it? But we're not going to have that luxury over here, so we will just assume that it works. And if disaster strikes, okay, I have a backup plan, which is to give you sample images. Okay? But we'd like to get your images to come out, as they say. The amount of film that you need is probably, now, the amount of film depends on how well the camera runs. It is, I think maybe it's superfluous to say that if you have this drum, which is turning 5,000 RPM, which is, by the way, higher than the spec speed for this drum. You'll see that on Wednesday. And the film is taped on the outside. Centrifugal force is going to make that film try to leave the drum, right? Well, if the film isn't attached just right, there is a tendency for that film to fly off, and if it does that, well, you put another load of film in. So it'll be interesting to see if we can keep the film on there. But probably, I mean, you're only using a foot of film. And, well, maybe a foot and a half per load. So even if one goes awry, you know, a 20 exposure roll or 24 exposure roll should be enough for at least 2 runs. Okay.
Are you going to show us how to
Yeah.
sync the RPMs? Like,
Yeah, I'll have it all set up for you. We'll set it up at the beginning of the lab.
okay.
And you'll see how the camera is going to be lined up and how you determine the speed, and you'll be able to set the speed for your own project and so on. Yeah. One thing for the film, you should have a place to store it in after it's been exposed. So some of the cassettes that you get, the plastic cassettes, are not light proof. Well, think about something else to put them in until you get to the lab. And when you get to the lab, tell them that there's raw film in here, so they don't open it in daylight, thinking that it's a cassette. Anyway, it's a neat experiment. There are many ways to figure out the rate at which a bullet is traveling. But because we're in a high-speed photography experience, you know, we're going to do it photographically. Any questions?
What kind of film is delivering?
400 speed?
What?
Anything. 35 millimeter. If you want to process it yourself, if you want to do black and white and you process it yourself, that's fine. If you have left processing behind in your lifetime, In that case, take it to lab, and that'll probably be a color lab. Any other questions? If I can think of any answers without being asked a question, I will send you an email. All right. Okay, so see you next Wednesday, or this week on Wednesday.